SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We have been discussing about the banded iron formations as a major source of iron, constituting the major iron deposits of the world. And in course of discussion, we just started to look into the hypothesis on the origin of such deposits, and we are trying to look into some of the intriguing aspects, such as the depositional, the source of iron, and also in addition we do also have to give an account of the source of silica. Silica solubility also is very much depends a lot on the chemical environment in which the system is, and we also take it that the silica is also derived from the continental sources as well as the marine sources, the seafloor rocks or the sediments that are depositing there through the interaction with the water, which had a much more dissolving capability than the present day seawater, and that's how we get them deposited in the form of alternating layers of iron and silica, the issue which will be coming to in a while. But let us have a brief idea about the depositional environment briefly, that what is interpreted from the study of so many of deposits all over the world. So, if the depositional environment also can be looked at for the different types, the algoma type deposits with their association with the older greenstone belts, and then the depositional environment also could be thought of in reef related seafloor where there has been exhalations, volcanic activity, deposition of chemogenic sediments, and the lava. So, there the domains in which these iron deposits are supposed to have deposited during that time, and later on modified, deformed and metamorphosed in the later time as we see them in most greenstone terrains. So, they can be thought of as environment very much akin to the seafloor rifting environment in which we have the volcanic activity and the exhalations. The superior type, they are the stable shelf, as we just discussed through the diagram on which we looked into the hypothesis in which the bottom water or this seawater, the column of the seawater which had higher solubility of iron because of the low pH, because of the acidity that we have in the iron, the redox and the redox condition being so low, with iron being mostly held in +2 state, and there could be many possible ways in which the iron could be held in solution, either as +2 state in terms of Fe dihydroxide soluble kind of compound, or could be as bicarbonate. There could be many possibilities. Even the seawater could also have had a lot of iron in the form of chloride complexes, on which we are not going to get into the details, but the environment of deposition is somewhat is clear that it is a stable continental shelf kind of environment, but then they are associated with, there are some volcanic members which sometimes have to make some modification to the deciphered environment. And then the Rapitan type, they are the continental, type basins, reef bounded continental basins, where they are deposited mostly in the freshwater conditions in the intercontinental rift basins, and they are often in the type area. They are associated with the glaciogenic sedimentation, member representing the glaciogenic sedimentation, but that may not be genetically quite related to this basin, but the dominance of the oxide facies of the iron formation dominated by oxides, the situation is somewhat different from that of the other two, and they are not associated with any volcanic member representing any volcanic activity. Okay. Now we could now see that if the world ocean had a very high solubility of the metal iron held in huge amount in +2 state, then what could be the possible mechanism by which we could have brought about the deposition in the form of the iron oxides that we see in the ores, which are our banded ore with alternating layers of silica and iron oxide. So we could think of possibilities such as photooxidation. We could simply there are situations in which it could be direct oxidation or photooxidation. Direct oxidation could be represented by simple reactions as Fe2 plus oxygen plus water, because we are taking this to be a aqueous species. So you will have Fe2O3 plus we can have H plus. So it does indicate that such kind of mechanism which we propose for the we can balance this out, or we can even think of it could be in a process where it could be 4 Fe2 plus aqueous plus O2 plus 6 H2O giving rise to 4 FeOOH plus 8 H plus. It is this, as we have already stated, this is more probable or more realistic in the initial process of deposition of the iron, because we are getting them deposited in an aqueous environment, and there is liberation of H plus ion, and it goes without saying that this kind of a reaction will only proceed if this H plus ion is able to be consumed. That means the condition prevailing would be a little bit more alkaline, which we can always visualize that is happening in a shallow self region. So this kind of a mechanism which we could propose for the oxidation, direct oxidation with increased partial pressure of oxygen. This oxygen partial pressure we have already discussed that this increase in the partial pressure of oxygen is because of the increase in the existence of the photosynthetic organisms which liberated oxygen, with the gradual increase in the oxygen concentration in that aqueous environment. That's actually the prime mechanism by which there has been extensive deposition of iron in that particular period of time, and which never happened again because the conditions were not conducive for having that much of amount of iron held in solution by the world ocean. It could be a direct it could be a photooxidation, by the ultraviolet light. So we could write Fe2 plus aqueous plus 3 H2O plus we will represent the ultraviolet light as H nu, giving rise to Fe OH3 plus 2H plus 0.5 H2. This reaction of course will be still more schematic, but it will not require that much of a rise in the concentration of oxygen. but only the availability or increasing intensity availability of the ultraviolet light that would, so it would look to be a mechanism. As a mechanism, it would look to be less efficient or less probable than the mechanism which is shown, which is supported by the increasing oxygen content. This will only be interpreted in a way that the ultraviolet, because if we involve a huge amount of iron 2 plus getting deposited as hydrated oxide of iron and absorbing the ultraviolet radiation from the sun, then it will enhance the growth of organisms in the aquatic environment or on the land during that early time, and possibly that's how the organism started to proliferate, but that's pretty hypothetical. It could be one of the mechanisms by which one can have this deposition. Then it's in our discussion about the origin of this very interesting and important class of deposit giving the bulk of iron requirement is the banding, which we saw the photograph. They are very persistent, they are repetitive, innumerable, there are innumerable cycles of such kind of layers which can be called as mesobendings, because we can see them in hand specimen in the scale of several millimeters to centimeters, and they are alternating silica rich and iron rich layers. So as one of the things to be explained about these deposits, the banding is something which is also need to be understood. So we can consider many possibilities. First is that the source, it could possibly be that there could have been alternately iron rich and silica rich input into the ocean because of fluctuations in the climatic conditions where the oxidation state at the very beginning. It might have caused in the quantum or the magnitude of input of iron and silica could have possibly varied. The other possibility could be most on the depositional side. Each individual pair of layers of a iron rich and silica rich, of course the silica rich layers are also ferruginous, they are the jaspers or the chatty layers, they are known as charts. So if we take them, the iron rich and the silica rich, a pair of layer to be constituting one varp, then there has been suggestion that possibly they represent one annual by the time taken for this kind of deposit comparing to varps which form in different lakes as we see them in the present time, they were interpreted as annual varps. Even it was proposed that there could also be representing daily varps, means during the daytime when there is availability of the ultraviolet radiation from the sun, the iron oxide rich layers will precipitate, and during the night time when there will be dearth of there will be no much of ultraviolet light coming from the sun, night time, so it will be the time during which the silica will precipitate in form of the cryptocrystalline silica layer which we call a jasper. But then they will also have their shortcomings in this kind of explanations because they are being deposited in an ocean basin. The other possibility is that they are both the iron, because when we are considering the iron to be precipitated in the form of the hydroxy oxides, they do essentially they happen in the form of gel or the colloidal kind of precipitation. As we see them, many of the preserved samples where the colloidal precipitation of iron oxide in the form of goethite in many alteration zones, which is see that they are essentially colloidal precipitation. So they could be that since both silica and iron are precipitating as colloidal precipitates, but they require different conditions for what we can be called as an isoelectric point, means the pH at which the coagulation of this colloidal particle will take place. So this isoelectric point for iron oxide and silica are different, then it could explain that, well, basing on the particular pH value occurring in the aqueous environment because of the fluctuations, it could result in the alternate precipitation of the silica rich and the iron rich layers. So, this all that we could discuss about these very interesting and very important class of deposits which are our banded iron formations. As I told you that there are these are the class of deposits which have been extensively studied, and the older deposits, when there are many features like many subtle chemical characteristics such as the rare earth element distributions and several other chemical parameters, many times many of the superior type ores, there are signatures of the deep sea water signatures which come from them, and also volcanic exhalation signatures. That is how many of the depositional environment are thought to be mixed type or hybrid type environment. And but the fact remains that they are a very interesting class of deposits, and they still generate there are many issues which still need to be resolved. And so that is all about we could discuss about these banded iron formations as a basic idea, basic knowledge that we need to have. We will discuss about them a little bit more when we see them about the enrichment process, because as I told you, these ore bodies, they do undergo, in order to be mined as high grade ores, which generally is done in many of the countries including India. So, the high grade or where the iron is more concentrated of the order of 55% or reaching to 60% or even more, that it requires some later modification enrichment processes by which we could possibly remove the silica layers, and which many types of, in the mining geology term, there are many ways they are called as lumpy ore or blue dust and this blanket type of situation in which the high grade ores are exploited. So, that is all about the banded iron formations. Now, let us move on to it's also be the discussion will be brief in order to have within the constraint of time. So, we do have manganese. We all know that manganese has a very similar geochemical affinity with iron, and manganese also forms oxides. The only difference that manganese has with iron is that manganese does not form a stable sulfide, even though its name we all know it is alabandite, but it is generally not observed or not seen in nature in any of the ore deposits of manganese. But manganese exhibits a wider range of oxidation states from +2 to +7, and occurs the mineralogy of the manganese ore is far more complicated. I mean, lots of oxide mineral phases which are present for manganese compared to iron. But the fact is that since iron and manganese are both geochemically very similar, so they would have also followed the similar type of geochemical cycle from the very beginning, and they also are likely to have been eroded, transported, and remained acquired by the solution, and also to have been deposited in the basins, much like the banded iron formations, and that is what exactly we see them. Most of the older, because we know that in the greenstones we do get manganese deposits in close proximity with iron deposits. In superior type provinces like the Superior province, or in the iron ore craton in India, and many other basins where we get the superior type of iron deposits, we get manganese in very close association. And the way we describe the manganese to be occurring in different phases as oxide, carbonate, and carbonate phases, just the sulfide will be missing. We also do get them as oxide and the carbonate ore, which is the carbonate is rhodochrosite. So, both exist as oxide and carbonate and silicate phases also. And in addition to the sedimentary iron, sedimentary manganese deposits, manganese also does form rich deposits by residual concentration process from many high grade metamorphic terrains where there are metamorphism of the manganese rich sediments, and later enrichment process have given rise to very rich deposits, which we are not discussing here. Maybe we will take them up in the discussion when we will be taking up the mineral deposits of the Indian subcontinent. As far as this particular issue is concerned, when we are discussing them together, it would be worthwhile to see the characteristics of these here by looking at these two diagrams which are just nearby. So, if iron and manganese have got similar geochemical affinity, then it would be good to see, or it would be worthwhile to see how their oxides or how their species plot on the EH/pH diagram that we generally extensively use for iron, and we also do use for manganese. What we see when we compare these two, we find that okay, this pyrite field which I showed, that the diagram which I just drew in hand, the stability field, this is iron 2 plus, iron 3 plus, and this is hematite, this is magnetite. Magnetite, when it is a silica rich situation, it might be a iron being silicate, and the area that this pyrite stability field has in iron 2 plus and carbonate, depending on what is the dominant sulfurous species here, whether it is a sulfate or a sulfide or a bisulfide, and we see these stability fields. So, what do we see is that they are more or less comparable. This is the stability field of manganese 2 plus, and this is rhodochrosite, and this is the stability field of hematite, which very much coincide with that, and this is the pyrolusite field. So, what essentially is observed is that manganese only requires a little higher, because this is the hematite field and this is the manganese carbon field, this could be compared. So, manganese only requires a little higher oxidation state to form its oxides, and in under any given situation, iron is much less soluble than that of manganese. Manganese persists in the solution for longer time and also till higher EH conditions. So, that is the reason why in most of the basins we find that the manganese bearing horizons generally succeed the iron bearing horizons which occupy the lower part of the stratigraphic column. And so, this is the reason which for example, as we see that there are comparable stability in surface environment. For the manganese has only as a higher solubility. Older deposits occur in close proximity, while the young Cenozoic deposits, like the ones which are occurring in the Black Sea, which is a very interesting situation, where Black Sea is essentially a stratified sea because of the salinity difference, and is a lower, the bottom part of it is pretty low pH and acidic eugenic conditions, and it's exactly a basin where the present day situation can be studied. The concentration profile of the two iron and manganese, where the bottom water is very manganese rich, and the same situation is visualized that the bottom water is upwelled periodically and encounters higher EH conditions, oxidizing conditions, where they get deposited in the basin rims, or the edge or the self part of the basin has rich manganese deposits, as we see them in the famous Nikopol deposit in Ukraine, just around the Black Sea. They are Cenozoic deposits, but these deposits are not associated with any rich iron deposit, which comes out as one of the major point of distinction. That is possibly explainable on the basis that iron is not as soluble as manganese in the present day prevailing physicochemical conditions, the seawater, the pH and the oxidation state, the partial pressure of oxygen in the atmosphere, and that is the reason why, or any amount of iron which will be there dissolved in a situation like a Black Sea, stratified Black Sea, will be deposited on the floor as sulfide, where the condition is very reducing, and we will be only getting the manganese deposits at the upper horizons. So, we go to a very interesting situation here. Is also that the manganese situation would have rather remained incomplete if we do not discuss something about a very interesting occurrence of manganese in the form of what we call them as nodules. They are essentially ferromanganese nodules, and they do have a latitudinal restriction, if you could see here. They are distributed in almost all the seas, the Atlantic, the Indian Ocean, the Pacific, where we could see that the They are essentially ferromanganese nodules, and the concentration of the black dots are representing higher value than the open dots. These ferromanganese nodules, as they are called, are more richer or more considered as more important as a resource of nickel, cobalt kind of metal, and sometimes even some of the radioactive metals like radium and uranium, rather than the iron and manganese, because compared to the iron manganese which we have the land based resources which are in plenty. So these manganese nodules, they have definitely are very intriguing, because one has to explain as to they are observed on the open ocean, the sea floor in great depths, and the only precondition possibly is that they be in areas in the open ocean where the rate of sedimentation has to be low for the manganese nodules to grow. Here is a picture as a cross section or as a section of a manganese nodule. That is why they are called as the nodules of the concretions. At the core of it will be any particle, either an older nodule or any kind of a dead turtle particle from the ocean floor, or any animal teeth or kind of organism, any part of a hard part of any organism, on which we will have this kind of a concentric colloidal precipitation of the manganese, mostly manganese oxides with variable concentrations of iron. They are observed on the flanks of the mid-oceanic ridges. They are also observed on the sea goets, the sea mounts, and there is a bit of a correlation on their cobalt content. When they occur on the cobalt content generally on the flanks of the mid-oceanic ridge or on the sea floor mounts or the sea goets, the cobalt concentration is higher compared to the ones which are found in the sea floor, and they are kind of can be projected as the resources that are there for future, because right at this point of time the technology to mine them out from the sea floor has not very well in place, but they do have a substantial amount of the metals as reserve of the metals available as a resource of the sea floor, which we will also be discussing a little bit when we go to the sea floor resources. So they have been pretty interesting and still not very well understood as far as the origin is concerned. The metal, the obvious source for this metal like manganese could be the sea floor, rock on the sea floor itself, exhalations coming from deeper and the regions in which there are higher temperature, in which the water is reacting with the sea floor rocks and getting enriched with respect to manganese, and some very special situations in which they may be depositing, because otherwise in general the sea floor situation would not be that very oxidizing in nature to favor the growth of this kind of nodules. There must be some additional factors, even some biogenic factor also cannot be ruled out, and people have also attempted to calculate the rate of growth of this manganese nodules, which are pretty slow. Here there is a picture of the manganese nodules which are recovered from the Central Indian Ocean Basin by NIOT, National Institute of Ocean Technology, and so they do constitute the modern day they give us an idea about the present day formation. When we talk about whether ore deposits are forming in the present day, they are a very good example for us, in addition to the fact that they remain as a very rich resources not only for iron and manganese but for rare metals like nickel. I think the total nickel resources that might come from these manganese nodules possibly will outweigh the resources that is available on land as far as discovered so far. So that's all about the iron manganese, and they are of course essentially have to be chemogenic, and they are classified under that category. So we conclude our discussion on the chemogenic sedimentary process giving rise to the important metals iron and manganese. Thank you.